To begin, I actually wanted to tell you a small story. So this is a story that is recounted in Robert Macfarlane's book called Landmarks. He is a British nature writer that I absolutely love, highly recommend reading him. So in this story, he recalls inviting his mentor, Roger Deakin, to come to Cambridge and give a talk. And his hope is that Roger will give an amazing talk and everybody will think that Robert is a wonderful person as the mentee, because the mentor is so great. And here is his recollection of that moment. So he says, "I stared dedicatedly at my shoes, embarrassed that my friend was failing to perform in front of my academic peers. It was only later that I realized that it wasn't a failure to perform, but a refusal to conform. Cambridge seminars expect rigor and logic from their speakers, a braced subtlety of exposition and explanation, tested proofs of cause and consequence. But water, which was Roger's subject, does not do rigor in that sense, and neither did Roger, though his writing was often magnificently precise in its poetry. For Roger, water flowed fast and wildly through culture. It was protean, it was slipshape, and so that was how he followed it. Slipshod and shipshape at once, moving from a word here to an idea there, pursuing water's influence too fast for his notes or his audience to keep up with, joining his watery subjects by means of an invisible network of tunnels and drains." And I love many things about this story, but I really want to focus on that last bit. So joining his watery subjects by means of an invisible network of tunnels and drains. So Roger is giving a talk about UK waterways, which is his subject of intellectual inquiry, and he gives the talk in the same manner that his subject works, in this sort of flowing, watery way. And so I wanted to ask the question, is that something that is more general? And I think it actually is. So I think knowledge itself, not just knowledge about UK waterways, but knowledge about just about anything, is a network and has a particular network architecture. This idea is not new, necessarily. So Henri Poincaré pointed out in his 1905 Science and Hypothesis, the aim of science is not things themselves, as the dogmatists in their simplicity imagine, but the relations among things. Outside these relations, there is no reality knowable. So that's sort of a gesture in the right direction. And then Dewey, in his 1916 Democracy in Education, I think hits it on the head when he says, knowledge is a perception of those connections of an object which determine its applicability in a given situation. Thus, we get at a new event indirectly instead of immediately by invention, ingenuity, and resourcefulness. And ideally, perfect knowledge would represent such a network of interconnections that any past experience would offer a point of advantage from which to get at the problems presented in a new experience. Okay, so knowledge is a network in some sense. Now, let's make this a little bit more practical and imagine that I am at Penn, I'm giving a lecture to the undergraduates in my class, and I'm faced with this common problem. I have a network of knowledge in my head. I have, let's say, 15 concepts that I'd like to transmit to the class, and those 15 concepts are related to one another in a very particular way. And my challenge is that I need to take this network architecture and transmit it to the student in a way that helps them to understand what the relations among those ideas actually are. Now, why is this hard? It's hard because I have to do that while obeying time. I would love to disobey time, but that doesn't tend to work for me. So what I need to do is to say one word in front of the next, pass through one idea in front of the next, but somehow in that linear, unidirectional transmission, I have to give them this, which is nonlinear and not unidirectional. So here's the problem. Here is the brain of the speaker or writer over here on the left-hand side, and we are faced with the challenge of mapping this potentially high-dimensional network architecture into the one dimension of time, because I need to string out concepts one after the other, in such a way that the brain of the listener or reader can optimally reconstruct what that network architecture was. So there's many interesting questions here. How do I figure out what this network should look like? What am I actually trying to explain? How can I map it into the one dimension of time? And how does this person on the other side optimally reconstruct from a linear sequence this high-dimensional knowledge? Okay, so this sounds hard, but we do it all the time. And in fact, this capability that humans have to infer patterns of pairwise dependencies between bits of information from incoming streams of data allows us to do all sorts of things. So it allows us to learn language, to segment visual images, to parse tonal groupings, to parse spatial scenes, to infer social networks, and to perceive distinct concepts. So this is a much more general capability that we have, and the big question that I had is, how do we do it? And how can I, as a scientist, study how we do it? So can I come up with a very simple experiment that I can do in the laboratory with human participants that will help me understand how we infer these network architectures from continuous streams of stimulus? So what I'm going to do is that I'm going to have this beautiful network here, and I'm going to allow the nodes inside of this network to be words or images or movements. And then every edge in the network indicates an allowable transition between nodes. So in other words, I can pass from idea 13 to idea 12, but I'm not allowed to pass from idea 13 straight to idea 4. I need to pass through a few intermediate ideas first. Okay? Then what I do is that I construct a sequence of stimuli by taking a random walk on this graph. So I'll pass along any of these edges that actually exist, but I won't go through the white space. I won't go through disallowed edges. And then I will ask human participants to perform a simple task at each stimulus so that I can measure their time to react. And the reason that I do that is that their time to react is an indirect measurement of what they're expecting. So if the human is learning this network, then they will respond relatively quickly when I ask them something. And if they're not learning the network or not expecting that transition in ideas or words or movements, then they will be very slow to react. So from the time that it takes them to react, I can infer, were they expecting that? Did they learn that transition? Or did they not learn the transition? Okay? So we can instantiate this problem in a couple different ways. These stimuli can be movements, they can be visual images, they can be social content, and we've studied many of them, but I'm just going to tell you about the motor version of this because that's a little bit simpler to explain in a short period of time. So what we have is a sequence of stimuli here. This one stimulus is 5 boxes with 1 or 2 of them colored, and that indicates to them which button on a little keyboard they should be pressing. So this means press the 5th finger, this means press 1 and 3, this means press the 3rd and the 4th finger, this means press the 5th finger, press the 2nd finger, and press 1 and 4. And this sequence has been defined by taking a random walk on this graph. Now, random walks have really beautiful mathematical properties, so that allows us to build mathematical models of their expectations. And then this is their hand placement on top of the keyboard. Okay, but before we get into the discoveries that we're making, I want to ask the question of what do we already know about this problem? Okay? So what we already know about this problem is that humans are very capable of understanding how probable a transition is. So if I am at A, and I see that 75% of the time I go to B, then anytime I see A in the future, I will expect that B is coming next. Humans are quite good at that. Alternatively, if I am at A and 25% of the time I move to C, then I will expect C to happen sometimes when I'm at A, but not as much as I'm going to expect B to happen. Right? So we understand transition probabilities, and we learn them very quickly, and then we predict something about our environment or what's going to come next based on those probabilities we've experienced before. A corollary to that capacity that humans have is that if you are at A and you've only ever seen 2 options after A, then you would expect each of those options 50% of the time. I'll expect option 1 50% of the time, and I'll expect option 2 50% of the time. If I am at A and I have seen 3 different options come after A in my long history of experience, then when I sit at A again, I'm going to expect option 1 33% of the time, I'm going to expect option 2 33% of the time, and I will expect option 3 33% of the time. So in other words, when you are sitting at a current experience, if you know that many different things may come next, you will be very uncertain about what the future holds, and therefore you will sort of respond slowly because you don't know what's coming next. However, if you always know that lunch comes after breakfast, then when you're at breakfast, you know with 100% certainty that lunch is coming next, and so you won't be surprised, all right? And you will act very quickly when lunch happens. All right, lunch is coming. All right, so can we actually see this in human reaction time data from the experiment I just described? The answer is yes. So here what I'm showing you is human reaction times in milliseconds, and along the x-axis is the entropy of this place where you're currently sitting. So if I'm sitting somewhere and only one option has ever come next, then that means my entropy is down here at 0, and humans respond very quickly because they know precisely what will always happen next with 100% certainty. Alternatively, if you're sitting at a spot where you've seen 14 options come next from that position, you're very uncertain, and your response will be slow. And so that's what we see here. The reaction time is much higher when you're sitting over here. Okay, so this slope is quite tight. It indicates that in this particular kind of experiment, humans are processing 1 bit of information in 32 milliseconds, which I think is kind of amazing. Okay, but I wanted to ask the question of whether humans are just sensitive to entropy, which was sort of known previously, or whether we're sensitive to something more. Are we sensitive to the higher order network architecture? So I'm going to go back to this picture again. And now what I'm plotting on this network is human reaction times on this task. And what you can see is that humans have the darker blue reaction times, so they're slow, or they're faster inside of one of these little modules, and then they're slower at the transition between modules. Okay, so this was actually extremely surprising to us and is a marker of human bias. And for you to understand why that's the case, I want you to note that every node in this network has exactly 4 edges coming out of it. So when I sit at any node, I have a 25% chance of going this way, 25% chance here, 25% chance here, and 25% chance here. So if all I perceived was the probability with which things are coming next, I would be equally swift at all of these transitions. So technically, what we would have expected was the exact same color, the exact same reaction time over every edge in this network. But that's not what we see. Humans are very slow at these transitions between clusters. So the big question is, why are they doing that? That's a bias that you would not expect to happen, and suggests that they're perhaps perceiving the higher order clustering structure. But that's not the only thing that humans are sensitive to. If I actually take that same graph, that same network, and I look at the reaction time inside of this tiny triangle that's up at the top, or in the purple lines, which are sort of intermediary, or this cross-cluster transition here, we are differentially sensitive. So here is the reaction time for humans. If we compare the purple and the blue, so that's inside of the module, we can see that humans are slower in the purple edges and fastest in the blue ones at the very tip. And here you see the difference between the red and the purple, so that's this cross cluster and this one. You see, and here is the difference between the red and the blue. Consistently, you see this difference in reaction time, which means that humans are fastest in this little top corner. They're a little bit slower on any of these purple edges, and they're even slower along this red line. Okay, so this is a human bias that's not just about clustering. It seems to be something more about the hierarchical structure in the network that they are exposed to. It's interesting to ask how that could potentially impact their understanding in a learning environment when I'm giving a lecture on certain topics. But before we address that question, we wanted to ask, is this sensitivity to the architecture of the network underneath of the stream of stimuli something that depends on the actual organization? So what I'm showing you here is that same modular structure, but I didn't have to show that architecture. Maybe I wanted to show something that's a little bit different. So perhaps I have random ideas that I would like to transmit, or perhaps I have ideas that are organized more in a cycle or a circle. And this is a lattice graph that allows me to transmit that kind of architecture. And we ask the question, are humans equally swift at responding in this case, and in this case? And the answer is no. In fact, I've ordered these along swiftest response, medium response, and slowest response. So if you are listening to a lecture that has random ideas connected also randomly, you will probably be relatively slow, right, in understanding what the person was trying to say. Alternatively, if the information is presented in this modular way, then you may be better able to understand it. That's sort of the overall idea or an intuition that could go along with these data. Okay. So that is interesting. It suggests, number one, humans perceive something about the network architecture, even from just a continuous stream of information that's linear, unidirectional, right? So humans can do this, but they do it in a really interesting biased way. Biased in the sense that they seem to be swiftest inside of these clusters and slow on the boundary between clusters. Okay, so now, as I move to the next section, we want to ask the question of why or how humans do this, what's going on in their mind when they're doing that. And I want to motivate this second part with this passage from Arthur Benson's biography of John Ruskin, called A Study in Personality. And he says, you know how most of us in idle moments, or perhaps even more in moments when we are officially supposed to be occupied, lapse into reverie in which a stream of thought, it may be placid, it may be vehement, sweeps through the brain from the flushed reservoir of the mind. Suppose you check yourself suddenly in one of those reveries. Try to put in words what you have been thinking of, and as you thought it, you will find that it is ludicrously impossible. Half the thoughts have passed without clothing themselves in any vesture of word. One thing has suggested another, often enough by some trivial similarity of superficial form. The whole thing is evasive, elusive, and irrecoverable. So what are people thinking? I think what's happening is that much of this is not being clothed in word. There's a passage, a perception of information that's not being codified accurately. So here's our little human here. And in order to build an understanding of that network, they need to be able to link what they just saw to what they are currently seeing. So here is time, and here's what they're currently seeing and what they just saw. Now, if they accurately remember precisely what happened just before as what's driving what they are currently seeing, they will build an accurate assessment of the network itself, and they won't have this bias. So that's definitely not what humans are doing. What we think they are doing is that they are trying to maximize their accuracy in this task, but also minimize the complexity of the computations that they perform. So humans are a little, to some degree, it's a little bit, it's not laziness, but it is trying to be as accurate as possible while only using the computational resources that are absolutely necessary. So we can build a mathematical model of that. I'm not going to go into the details. It's a free energy model, and the distribution that minimizes this free energy is the Boltzmann distribution, just for any physicists in the audience. But I'm going to give you a picture of what that means. So here is our human right here. If he or she imagines that anything in the past has driven what he is currently seeing, then his perception of the network architecture is this big hairball, which basically says that anything in my experience could be driving what I'm currently seeing, okay? If, on the other hand, he or she accurately remembers precisely what happened in the moment before, as driving what he's currently seeing, then his perception of the network architecture will be absolutely perfect, and he won't show any of this bias that we actually see in humans. In between, there's this person here who tends to remember what just happened as what's driving now, but has some non-zero probability of remembering anything in the past as driving now. But that probability falls off with time. And if this is the case, then the perception of the network architecture looks like this, where you have strong expectations inside of these modules and weak expectations on the boundary between modules. So what this suggests is that this simple sort of forgetting, not perfect memory, but also not zero memory, is a simple explanation for this bias in human perceptions that allows them to see the cluster organization in place of the perfect transition probabilities. Now, when we've built a theory like this, as I said, it's sort of a formal mathematical theory that I didn't go through the details of, we want to estimate the parameters from the data, validate the mechanism of the phenomenological theory, use the theory to make a prediction about something in a new experiment. And I'm just going to tell you we did all that and it all works, but I'm going to leave it there. And it just gets to my last point, which is this more than just this simplified laboratory experiment that I'm describing to you? Is this something that is relevant for human experience much more generally? And to motivate that last question, I wanted to quote Joseph Glanville's The Vanity of Dogmatizing from 1661, where he says, "But how is it, and by what art, doth the soul read that such an image or stroke in matter signifies such an object? Did we learn such an alphabet in our embryo state? And how comes it to pass that we are not aware of any such cognate apprehensions, that by diversity of motions we should spell out figures and distances, magnitudes, colors, things not resembled by themselves, we attribute to some secret deductions?" So how is it that we use symbols, languages, different types of representations of information to communicate and talk with one another? Perhaps this is more than just lectures. So to study information processing in real networks, expanding much beyond what I've told you so far, we studied some language networks. We took all of the works of Shakespeare, of Homer, of Plato, and several other authors. We took semantic relationships in the Bible, Les Mis, some glossaries and thesauri, the World Wide Web as a place where we gather information. And then we also took two kinds of alternative communication systems through social networks and also through musical compositions. And we asked the question of how humans perceive information through these different network architectures. We defined the perception of the information as a combination of the entropy, which we talked about at the beginning, so humans are sensitive to entropy and how complex the network actually is, but also how different is the network architecture from what we would expect. In other words, how biased would we expect to be as humans? And again, there's some really beautiful math behind this that I'm going to just skip over. And here are the data. So each of the colors here indicates a different set of real communication networks. So in blue are the language networks, in cyan are the semantic networks, in green are the World Wide Web, and then in red and purple are social interactions and music or transitions between notes in musical compositions. And what I want you to notice is that the real entropy is down here on the x-axis and the entropy of a random system is on the y-axis. All of these communication systems sit below the equality line, which means that all real communication systems are packed with information. The entropy in them is much higher than you would expect if this was a random system. And then on the right-hand side, I'm showing you the divergence from human expectations. So here's the real divergence, and here's how much you would expect in a random system. Notice that all of these human communication systems are above the unity line, which means that they are less different from what we would expect, our expectations, given our human biases. They're closer to our expectations than a random system would be. And here you can just see that separately for each of the different kinds of information. I want you to notice that language has the most entropy, so it's packing in the most information in the smallest architecture, and music and social systems, which are more about entertainment, seem to have a little bit less information and fit our biases even better, whereas language pulls us a little away from our expectations. So just in quick summary, humans can learn the architecture of networks underlying a continuous stream of information, which I think is kind of amazing that we can do that. Humans display expectations that diverge from the true network, but allow them to perceive this larger organization. Number 3, these biases in learning or large-scale perceptions can be explained by a poor memory or a sort of fuzzy temporal integration. And then number 4, real networks fit our biases. They have a low divergence from our expectations while packing in a large amount of information, so having relatively high entropy. And I think it's really interesting to ask why. Have we created communication systems that fit our biases? Or have those communication systems been created separately and our perceptions have just come around to fit them? Which happened first? And sort of on that note, I wanted to end with this passage from Aristotle's Metaphysics where he says, "Mind thinks itself because it shares the nature of the object of thought, for it becomes an object of thought in coming into contact with and thinking its objects, so that mind and object of thought are the same." And with that, here is the picture of the last few minutes. We started with Macfarlane, went to network learning experiments, took a hiatus across Benson, went through network learning theory, and then transitioned across Glanville to human information processing. Thank you so much for listening.
I see Bill over there. Oh, okay.
Thank you very much, Jeffrey Hamburger from Cambridge. I'll confess to not having understood everything with which you presented us, but I am an historian of diagrams. And
We have to talk.
so I was fascinated by the way in which your presentation employed and depended on diagrams. You ended with Aristotle, who of course also famously wrote that he couldn't think without images, and by images he meant diagrams. Charles Saunders Peirce said something very similar. And so I'm wondering, when you put together a presentation like this, do you think of the diagrams simply as visual aids? Are they a metaphor for what it is that you're seeking to describe? Or do you think, or does your research suggest that diagrams, understood in general terms, are really a map of human understanding? Because diagrams have this uncanny ability to simulate the patterns of thought. So I guess what I'm asking is, what is the ontological status of the diagram?
That's a hard question. So I will definitely say that I think I am using the diagrams, particularly the network diagrams, because I think that the relationships between these ideas are encoded carefully in the neural system inside of our head. There's some really beautiful work from Tim Barron's group at Oxford that shows that there are particular parts of the brain in hippocampus and entorhinal cortex that are coding for the distance between these items on a network. So I think it is the diagram is being coded there. So I think that suggests that that's relevant. But I think the other point I wanted to make actually is that there's a limitation to what I've shown you here, which is that I made the claim at the very beginning of the talk that I am only allowed to say one word in front of the next, and therefore the description is linear, unidirectional, and one-dimensional. But because I have used diagrams, we are at a higher dimension than one. So that's a limitation of what I've described. I haven't yet found a great way of encoding this as a second stream, but that's the direction that the work is going now.
Okay, you'll be working on that.
Okay.
Regna Darnell, University of Western Ontario. Apologies, I mumble. I work with relational systems of thought between indigenous peoples of the Americas and Western thought, whatever that is. And one of the things I worry about is individual variability when we try to look at the ways that one can process relational information, which there's more expectation for in some cultural systems than others. Could you comment on that?
That's very interesting. Our work has not directly addressed differences in cultures in this particular kind of learning, but I will say that there is very much individual variation in our human participants. And so actually, if I went back to this picture, we find that about 2/3 of our human participants are in the middle, and then the rest are either the sort of acting as if they have no memory from our perspective at least, so on the left-hand side. And then on the right-hand side, we have a few that are just absolutely perfect. Their reaction times are completely the same across the entire graph. So there are very interesting individual differences there. We have some initial data that suggests that it tracks with age and with gender, but I think that we need to unpack that a lot more before we make any claims.
Bill?
Hi, Bill Hook from Alexandria, Virginia, and I've got to say in the dozen or so years I've been here, that was probably the scariest talk here I've ever heard. Because
Yikes.
you're obviously very bright, and I'm thinking, boy, I'm glad I caught her at this point rather than 10 or 15 years from now. So a question for you. It seemed like you were saying the only reason for the difference in time is that the hearer's goal is simply replicating the pattern that the speaker is giving. But it seems to me that most people listening to talks like that are also thinking creatively. They're thinking on how to build on this, and maybe the delay is associated with, gee, I could rearrange these in some other way and go some different place.
That's a really great question. We have not considered the incorporation of other information from the human's current conception into their perception of this graph. But I do think that that does happen. I mean, when we are listening, we are constructing new ideas. The other related concept that I think I want to mention is that the human who is actually speaking also has a pretty large choice on their hands, which is what is the specific small set of interconnections that I want to show. Because honestly, if you each think about your fields and you think of 15 top ideas in your fields, if I asked you to explain the relationships between any pair of those 15, you would be able to tell me. So in your mind, that graph that you have is not this modular thing. It's a fully connected graph. You know the relationships between all 15 concepts, and they're actually important. And you have to choose what subset of those relationships you want to show in order to project a simplified view for the initial listener. But I agree that going beyond that and understanding what the listener is bringing is an important component that we are ignoring at the moment.
Fernando Pereira, Palo Alto. So in some of the diagrams, like the one over there, you have all these triangles. And we sort of know from cognitive science that triples are things that we can perceive instantly, unlike things would involve more complex structures. Could that affect the statistics that you are observing?
That's interesting. Let's see. Well, but because we're taking a random walk on that graph, you will end up spending a lot of time in triples, and that's going to strengthen those expectations, and you'll spend less time in large cycles, like around the center of the hole there. And so that will decrease your expectations. If we go to cycles of size 4, so squares instead of triangles, you will still spend more time there than you would in pentagons. And so that's going to strengthen your expectations there, but you may be slower than when we fill it with triangles. In a separate line of inquiry, we're asking if we take textbooks that we use at Penn and ask how do larger cycles, so holes, ever occur where we haven't closed triangles? And the answer is yes, they actually occur very often. And I think what happens when we try to teach a class is that we try to grow the information in a relatively homogeneous way so that we close all the triangles so the students understand, this goes to this, goes to this, I understand. But every now and then we pull in something that's farther away that creates a big hole, a big gap in your understanding. And sometimes that can be very motivating to the student, and it also gives them a foreshadowing of exciting things that are coming. So I think we use it in our teaching in a way that helps learning, but it's in competition with this nice closure of triangles that can consolidate the information.